Cool. So for the last seminar of the semester, we have Isaac speaking on his recent star paper, which is about using the planted Clique conjecture for public key encryption. So,
okay, thank you so much for the introduction. This is a joint work with Riddhi Ghosal from UCLA, Aayush Jain from CMU, and Amit Sahai from UCLA. Before jumping into things, let's just take a quick refresher on public key encryption. A public key encryption scheme consists of three algorithms. We have a key generation algorithm, an encryption algorithm, and a decryption algorithm, all of which are parameterized by a security parameter lambda. Now, the communication protocol goes as follows. We want Alice to be able to generate a pair of keys, a public key and a secret key. And she transmits this public key to another person, Bob, over an insecure channel. Now, Bob can use only the public key to encrypt some bit that he has, B, in order to produce a ciphertext. And then he sends this back to Alice, and she should be able to figure out what the bit was with high probability using the decryption algorithm along with her secret key. Now, critically, to have security, some eavesdropper Eve, who listens to the entire conversation and also has access to all of these algorithms, should have negligible advantage to guess the bit that was transmitted. One more quick note is that we only care about basic CPA security, which is the type of security I've just described. And from this, we can already get this secure form of communication. Now, you can imagine that public key encryption is a very important primitive for communicating between parties over an insecure channel or over some distance. But despite decades of research, we have very few sources of hardness known that imply public key encryption. I'll actually give a relatively comprehensive list just on this slide. So first, we have the schemes which are based on the hardness of factoring and the hardness of the discrete logarithm problem in various groups. But to our knowledge, all these assumptions that imply public key encryption are quantum broken. We also have some more newer assumptions based on things like multivariate polynomial systems and hardness of problems related to isogenies. But unfortunately, we don't have any rock solid assumptions as of right now that are also known to imply public key encryption from these categories. And then finally, there's assumptions based on linear codes and lattices, and we do have relatively good candidates in these categories. But something to note about all of these assumption categories is that they have strong algebraic structure. So this means that in theory, if we have a major advance in how computers can solve noisy algebraic systems, then some or all of these assumption classes could be broken. And in that case, we wouldn't even have public key encryption. As the saying goes, you don't want to put all of your eggs in a highly algebraic basket. So this leads to a natural question, which is, can we find new sources of hardness to get public key encryption? And one major goal is to build PKE from a variety of purely combinatorial hardness assumptions. And I use combinatorial here just to denote that they don't have any non-negligible algebraic structure to them. This research direction was pioneered by the work of Applebaum, Barak, and Wigderson back in 2010. What they showed is a way to combine a somewhat non-standard combinatorial hardness assumption plus some very mild conjectures from noisy linear algebra to get public key encryption. So the way to think about this, at least from my perspective, is that the real hardness is coming from the combinatorial assumption they use, and then they just have this very mild helper assumption from noisy linear algebra. I'll give some more details on this later. But the major open question from their work was, can we use a much more standard combinatorial hardness assumption in their framework? In particular, can we use the planted Clique conjecture?
I think one of the assumptions is sparse Albion, right?
Yeah.
And that's, I mean, I don't think there's any reduction on between Albion and sparse Albion. But that, arguably, you can also say is an algebraic structure.
Yeah, so this is work in the direction of trying to build public key encryption from combinatorial hardness. So of course we aren't there yet, but as I'll discuss later, this helper assumption from noisy linear algebra is not even close to being able to imply public key encryption on its own. But you're totally right. Yeah.
But this means that your construction still have this kind of noisy linear algebra.
Yeah, there's still this noisy linear algebra flavor. Actually, it turns out we're using noisy linear algebra in a regime that is related to sort of like PCP reductions and like high noise constraint satisfaction problems. Obviously, we're not like fully in that regime, but at least looking at it from an overall perspective, it seems to be somewhere in between these like strong algebras.
And you can work with more general random like local functions as opposed to linear, right? That's also true.
Yeah.
We have a dense minor sitting inside.
Yes, that's true. Yeah. So in our work, what we show is that yes, we can use the Clique conjecture within a similar framework to get public key encryption. So of course, the star of our show will be the standard Clique problem. We do need to assume mild quasi-polynomial hardness of this problem, and I'll give some more details on that in just a second. First, to establish what the Clique problem is, this asks to determine, given some random dense graph as input, whether we have randomly selected a small number of vertices and put a clique on those vertices, or whether the graph is truly just random. And what I mean by adding a clique is I mean we just pick those vertices, and then for every pair of vertices in our small subset, if they don't already have an edge between them, then we just add an edge. And we're assuming that no n to the log n to the alpha size algorithm can solve this problem. This is mild in the sense that we can take alpha to be an arbitrarily small constant. So for example, alpha equals 0.01 would be perfectly fine for our use case. And as I'll discuss later, this exact conjecture actually, and even stronger conjectures have already appeared in the hardness of approximation literature. For our helper assumption, like we've talked about, we'll be using the noisy k-LIN problem. This asks us to distinguish between a distribution where we have a sparse matrix A and then a noisy sample AS plus E of a random secret S. A little bit more details on this later. The other distribution is just A and then a totally random vector. So basically, you can think of this as distinguishing the case that we have a linear system where most of the equation, most of the constraints are solvable versus the case that we just have completely random constraints. And the key point here is that A will be a sparse expanding matrix. All I want to highlight right now is that the noise rate E that we can use is going to be far too high for building public key encryption on its own, as far as we know right now. To go into more detail about planning Clique, we'll first talk about what we mean by a random dense graph. For this, we're going to use the Erdős-Rényi model, denoted GN1/2. So this is the distribution over graphs where you have n vertices, and then for every pair of vertices, you add an edge between them independently with probability 1/2. So you just flip a fair coin. If it's heads, you put an edge. If it's tails, you don't put an edge, and you just do that process independently. We'll also use GN1/2 and then the clique size to denote the same distribution, but where we quote unquote plant a clique. I'll refer to this later as the planted Erdős-Rényi distribution. The only difference here is just what I was describing before. We pick a random small subset of the vertices and put all of the missing edges between them. Now, the planted clique conjecture is probably the most famous and the oldest average case combinatorial hardness conjecture. We have references going back to 1992, although it appears that it's been discussed in literature significantly before that. The conjecture says that no polynomial size algorithm should be able to distinguish between a graph drawn from the unplanted Erdős-Rényi distribution and the planted Erdős-Rényi distribution, but with two qualifications. The first is that the advantage can't be more than 1/3. So instead of negligible, we're saying 1/3. And we also need to take delta less than 1/2. So roughly speaking, the clique needs to be small enough. To discuss this 1/3, you might ask, well, why wouldn't we assume less than negligible? It turns out that there's actually a very naive algorithm, which gives us at least inverse polynomial advantage, even in the case that the clique size is just 2. This is to just count the number of edges in the graph we've been given. Because in the unplanted case, we have a certain distribution over the edge count. And in the planted case, we are only adding edges. So if you have a clique of size 2, well, we already expect to add half an edge. That's not going to make much difference, but it already gives you an inverse poly distinguishing advantage. And for this delta parameter, roughly speaking, if delta is greater than or equal to 1/2, this is the transition point between the planted structure being globally hidden and then the planted structure having a noticeable global effect. So when delta is greater than or equal to 1/2, we have efficient spectral algorithms due to Alone and co-authors to not only determine if there is a clique, but to actually find it.
So in fact, the algorithm is like, if you have root and log n, then you can just, in fact, do this naive algorithm, look at a vertex, vertices with highest possible degree,
Yeah.
highest list of vertices with like largest degree, and that because if you take a random edge which is connected to n of them, then you expect that roughly. Are you going to talk about this?
Yeah, well, that's actually related to this edge counting algorithm I gave here. That's the transition point where the edge counting, if you apply to each vertex, transitions from having just a small advantage to actually at least like. Actually, it has a very good advantage because you can imagine these two distributions spread out enough that really only the vertices in the planted clique will have very high degree. But that detail won't be important for us. Okay, and one more note is that for all delta greater than 0, so for all polynomial clique sizes, we do have an algorithm which runs in time n to the O of log n. This just follows from the observation that in a random GN 1/2 graph, we expect the largest clique to be of size only 2 log n. So we can just check via brute force if a set of, for example, 3 log n vertices induces a clique. And like I've discussed, we only expect this to occur if we're in the planted model. And you could just check this via brute force naively and n to the log n. Interestingly, this brute force algorithm appears to be near optimal in the sense that Barak and co-authors recently showed the sum of squares algorithm running in time n to the little o of log n fails to distinguish between these two distributions. The reason we see this as convincing evidence is because the sum of squares hierarchy is sort of the most powerful algorithmic framework that we currently know of for these types of random planted problems. Like I was saying before, we need to assume that the problem is hard for slightly larger algorithms, for example, n to the log n to the 0.01 size algorithms. But actually, this exact conjecture has already been used in literature. Specifically, a paper by Alone and co-authors assumed our exact hardness conjecture, and they actually take alpha equals 1/2 for most of their paper. They use this to get inapproximability results for densest subgraph problems. And more recently, Menarongsi and co-authors actually assumed that the sum of squares algorithm is basically optimal. They said that no n to the little of log n algorithm should be able to solve the problem. And from this, they were able to derive nearly optimal results for densest subgraph problems and also for problems related to Steiner forests. Any questions on planted clique? All right, and we'll move on to discussing our next assumption.
Maybe you can say why, like, if there are any PK from planted clique or Alone, or like,
Yeah,
what's that main difficulty?
Yeah, so we don't know any PK from planted clique just because while you can sort of maybe think of the clique as a trapdoor, nobody has been able to leverage that to actually get public key encryption before our work. And of course, we do need this helper assumption, which I'll now describe. In the noisy k-LIN problem, at a high level, we're conjecturing that no polynomial size algorithm should be able to distinguish between a pair of a matrix and a vector, where the vector is a noisy sample, the matrix times a random secret plus an error term, and another distribution where the vector is just taken completely at random. Now we say with advantage more than 1/4. Actually, the conjecture is even believable if we replace this with negligible, but 1/4 is all we need for our public key encryption scheme. The two main points are that A is sparse and expanding, and that the error vector E has noise rate inverse polylog, which is significantly higher than the uses of k-LIN to get conjecture on its own, as I'll discuss in later slides.
So what is it?
Yeah.
So sparse algorithm really works.
Yeah, with this. So this is actually known as sparse LPN in the literature, although generally when we think of sparse LPN, we think of a totally random matrix A. So we're saying that, okay, we can allow a little bit of structure in A, but it has to be expanding. It's also known as the noisy KXOR problem in literature, in the case that everything is over F2. This is just because you only have 0 or 1 values. So each sample is just an XOR of some bits from the secret. And there's one more perspective, which is from learning theory. You can think of each entry in this output Z vector as representing a noisy sample of the secret, because what is the Zi entry? It's just some row of the matrix A dot producted with the secret and then plus an error term. Yep.
The matrix A is drawn from some distribution, right?
Yeah, so in our conjecture, we're saying that A only has to be sparse and expanding. So it could be a worst case matrix.
Okay.
Yeah, well, although there are counterexamples to this, right?
Yeah, well,
Right.
the counterexamples are highly contrived, and we're outside of the regime of those counterexamples.
It doesn't matter what the sparsity of A is. Like, is it the same?
So the sparsity, what do you mean by that?
It's just not- Yeah.
Yeah, well, actually, I'll give formal details on that a little bit later, once we define expansion. All right. And actually, for simplicity in this talk, we're just going to consider matrices and vectors over F2. So indeed, it will be equivalent to the noisy KXOR problem. Now let's talk about this expanding word. We have a definition in terms of matrices, but this definition is kind of ugly. Let's instead think about it from a graph perspective. Okay, so we can map our matrix M, or a general matrix M, in our case for the public key encryption scheme, it's going to be the matrix A, to a bipartite graph, G subscript M. It's going to have a left partition, right partition, and a set of edges. We have one vertex in the left partition for each column of the matrix. We have one vertex in the right partition for each row of the matrix. And then we put an edge between a left and a right node, if and only if it corresponds to a 1 entry in the matrix. The bipartite graph is just encoding, in some sense, the 1 entries of the matrix. Now, when we look at this bipartite graph, we know that we want our matrix M to have exactly k non-zero entries per row. That means that the right nodes will all have exactly degree k. So it will be right k regular. In this example, we take k equals 3, so it will be right 3 regular. Any questions so far?
So in other words, right is the set of equations, left is the set of variables, and every variable, every equation is connected to k variables in there.
Yeah, yes, exactly. So let's look at this in terms of the matrix and the vector. Every right node corresponds to an entry Zi, which you can think of as a sample over its neighbors on the left side. And each of the left vertices is just representing an entry of the secret. Of course, the secret is unknown, so we can think of these as variable vertices and the right nodes as constraint vertices, which are linear constraints over their neighbors, but with some noise. Okay, and indeed, if we look at our matrix definition and translate it into this graph interpretation, we can see that the two conditions, the first condition about M having exactly k non-zero entries per row, just means, like I said, that the graph GM is right k regular. And now the expansion condition just translates to saying that any small enough subset R prime of the right vertices should have a very large neighborhood on the left side. Okay, so now we can plug in some parameters for our noisy k-LIN conjecture. We're going to take k to be logarithmic. Like I said before, the error rate to be inverse polylog. And we'll take the expansion cutoff t to be much greater than any polynomial in k or the error rate. In fact, we can take t to be so large that it's sub-exponential with respect to the arity k and the error rate. It will also be quite large with respect to n. Now, turning our attention to the second part of this statement, we say that A is a sparse 0.99 KT expanding matrix. And for this very large expansion factor 0.99, remember, like, the best possible that we could get is just 1. So we're already very close to the best possible expansion. we have strong sum of squares lower bounds, thanks to a work of Cathari and co-authors. And we also have immediate linear bias lower bounds. All right. To get some intuition as to why the problem should be hard, in this case, we can look at the challenges for a local solver. Let's say that we try to distinguish by just looking at a small number of samples. This would be a small number of right nodes or a small number of equations. But in this case, because we have such strong expansion, we have that those equations will cover many more variables than equations. So we get an underdefined linear system. And in fact, we'll actually have many like unique variables that only appear in one equation, which just means that we're totally screwed. But on the other hand, if we look at too many equations, in fact, more than t, which means that it might be possible to get more equations than variables, then we'll pick up a massive amount of error. Any questions on k-LIN before I move on?
Yeah, like here you described the intuition for the hardness of the problem, but is there like concrete cryptanalytic algorithm which have a cost, let's say, which depend on k or something? Like because you instantiate the problem with a k parameter, and you say that here the problems should be somehow hard from your arguments. But do we have, I mean, let's say, is it possible to improve like standard LPN algorithm for this kind of
Yeah, so as far as we know, people have actually looked at these exact types of expanding matrices. As far as we know, these algorithms can't be adapted. And like I was saying,
there's no even speed up, which is like, there is no, I mean, the atoms which have been made, there is no even speed up compared to standard.
The
Yeah.
speed up in the error probability is like super low.
Okay.
1 by n to the 0.5 plus delta.
yeah.
The really, only when the error probability is low. If the error probability is very high, as far as we know,
There
the
is
best
no gain.
attack is to find the fast vector in the kernel and then check the values.
Yeah. And actually, the attack Aayush is describing is precisely a linear bias attack, but
Yeah, it's
in our paper, we show immediate linear bias lower bounds for this problem. Yep. Any other questions?
Yeah, this is, I guess this is still related to the how to call it, the weight distribution of the dual code. And so
Yeah.
if the code is part, like we still have a good weight distribution.
Yeah. That's what the expansion
And
is telling
because
us.
we are showing large expansion, that means that the weight is large enough for the dual.
Yeah, well, and actually the expansion is so high that we can take even more naive arguments to just show that it's secure against known attacks. Okay, I'll give a quick discussion of related work. We do have public key encryption from just the noisy k-LIN assumption alone, thanks to a work of Applebaum, Barak, and Wigderson. They are able to leverage a totally random matrix A. However, they need very low error. In particular, the error rate is going to be an inverse polynomial, and it will actually exactly balance out with this expansion parameter. Whereas we're in a regime where the error is just way, way higher than, in proportion to the expansion parameter. More generally, Alupnovich back in 2002 showed how to leverage k-LIN in this dense setting, so that you can think of this as just standard random LPN. But he needed an error rate again, which was an inverse polynomial, this time in n. More recently, a work by Agarwal and co-authors explored ways to interpolate between this result by AVW and the result by Alupnovich, along with some new ideas, but they still cannot cross this inverse polynomial error barrier. And again, recall that we can take inverse polylog, which gives us a much higher error rate, and there's going to be much more errors across all the samples. We also have a few works on public key encryption from like noisier k-LIN in the same sort of regime that we're using, and planted assumptions. Like I discussed at the beginning, Applebaum, Barak, and Wigderson pioneered this field, but they needed to use a tailor-made planted assumption. A more recent work by Bogdanov and co-authors combined Goldreich's PRG, which we can see it as an analog of k-LIN, but with polynomials instead of linear constraints. But they still need a new planted assumption. For our result, we showed that assuming slightly higher hardness, of the standard planted Clique conjecture plus noisy k-LIN conjecture in this high error regime, then we get semantically secure public key encryption. To our knowledge, all the other schemes in literature either use a much less standard combinatorial assumption, or they can't make use of this high error rate. Okay, any questions about our result before I get into some technical details? I'll come back to this roadmap as I explain different key concepts. I put in black what we've already discussed, and the red stuff is all the conversion that we use to get from planted Clique and sparse LPN to public key encryption. First, I'd like to work backwards, so I'd like to talk about trapdoor expanders. This is composed of two computationally indistinguishable ways to sample a matrix A, such that if we sample the matrix from, for example, the first mode, then the matrix will have the strong expansion properties that we want. And if we sample the matrix from the second mode, then this expansion property will be completely broken by a very small compressing set. Looking at this from the graph perspective, we want that mode 1 will exhibit this small set expansion, but then mode 2 will have a very small trapdoor T of write nodes, such that the neighborhood of those write nodes is actually smaller than the size of the original set. Now I pause to make an important comment, which is that we're okay to bound the distinguishing advantage between these two cases by a constant. When we apply our whole construction, this allows us to build something called weak public key encryption. In weak public key encryption, we say that an eavesdropper might be able to guess some of the bits that were transmitted, but they still have some disadvantage. Like they still get a constant proportion of the bits wrong. And it's already known by a work of Hohenstein and Renner that we can turn any weak public key encryption scheme, as I've just described, into standard public key encryption with the standard notions of security. Okay, now I'll talk about how we use trapdoor expanders with sparse k-LIN to get public key encryption. This result is actually due to, again, Applebaum, Barak, and Wigderson. And the scheme is relatively simple. We'll sample the true public key to be a matrix A from mode 2. Remember, this is the mode that has that planted small trapdoor. And we set the error parameter eta so that we expect with at least constant probability that our planted trapdoor samples will have no error. Okay, and then for encryption, if, for example, we want to transmit a 0, then we'll set the ciphertext to be the matrix and then a noisy sample of a totally random secret S. And if we want to transmit a 1 instead, then we'll just send out the pair of the matrix and a totally random vector. For decryption, because of the way that we've adjusted the error rate, we can use Gaussian elimination on this small overdetermined trapdoor. Because remember, we have more equations than variables. Now, note that we might have some small decryption error, but this is totally okay to still apply the result that I discussed by Hohenstein and Renner to get standard public key encryption. And just one more comment is notice that in the case of a totally random with output vector R, because we have an overdetermined system, it's very unlikely that we'll find a solution. So just this Gaussian elimination does give us a distinguisher between the two bits. Now, probably the most important question is, why should this be secure? Because we mandated that the two sampling modes should be indistinguishable from each other from the perspective of an adversary, to someone eavesdropping on the conversation, the public key matrix A acts as if it were truly expanding. So another way to think about this is that even though the public key matrix has this tiny compressing component, the adversary doesn't know how to make use of it at all. And we can formalize this by a simple hybrid argument where we first swap the true public key for a matrix sampled from mode 1, and then we can apply the noisy k-LIN conjecture from here.
Are you somehow using this loss? Somehow you using the trapdoor expander as like a lossy trapdoor function?
No, we were generating just sparse LPN. Effectively, we wanted like the ciphertext is just sparse LPN sample. SA plus D, but you need to kind of decrypt, right? In order to decrypt, you need a sparse vector in the kernel, right? Because then you can multiply it with this, S times A will vanish, you get E times T, which is biased if the parameters are set appropriately. Now, the thing is, if you choose a run like, what you want is that in one case, there is like a small sparse vector in the kernel. In the other case, what you want is that there should be no such sparse vectors in the kernel. So what he's saying is that using a random graph, you'll be able to come up with using this clique assumption, you might be able to come up with an expanding sparse graph, where in one case you have no sparse vectors in the kernel, and in the other case, depending on the clique, whether you have a clique or not, you will have this kind of property where you have a sparse vector in the kernel, and if the graph is random, there will be no sparse vector in the kernel.
Yeah.
So that's
Yeah. And I'll give more details on this in terms of the graph perspective a little bit later. Returning to our roadmap, we can see that using the work of ABW and Polenstein and Renner, we can combine trapdoor expanders with sparse k-LIN to get public encryption. So the main technical contribution of our paper is to exactly show how to go from the planted clique conjecture to the existence of trapdoor expanders. For this, we'll leverage an intermediate object, which we call trapdoor non-compressors. Let's say that instead of enforcing true expansion, as per our gamma k type definition, we instead enforce a weaker notion. Here we want to say that for any small enough subset R prime of the right vertices, their neighborhood won't be too compressing. In particular, the neighborhood size can only decrease by a factor of f, where f is some small slack factor. More formally, we define this non-compression property very similarly to the expansion property. The only real differences here are that I've used D to denote the right regularity instead of K. And for the expansion, of course, we plugged in this slack factor instead of requiring a multiplicative gamma K increase. Now, a trapdoor non-compressor is defined very similarly to a trapdoor expander. It's just composed of these two ways to sample a matrix. The main differences are that in one mode, we want the matrix to satisfy this non-compression property. And in the other mode, we want non-compression to be broken, but now via a small, very highly compressing component. Looking at this from the graphical perspective, it's very similar to what we discussed for trapdoor expanders. Now I'll focus on this compressing component. Exactly how compressing do we need? Well, in a sense, we need it to be maximally compressing. What we mean by this is that for every set of D vertices in this neighborhood, we want there to be a corresponding vertex in T such that that vertice's neighbors are just the set we picked. So another way to think of it is that if we view the vertices in T as like representing hyperedges over the vertices in the neighborhood, then we want to form a hyperclique.
You want to find this set of equations which depend on like lots of variables.
Yeah, well, we're not thinking of these as equations yet.
But
yeah,
that's
yeah. It turns out that right now we want to maintain this sort of like cliquey property in our trapdoor non-compressor. And for the non-compression factor, we'll just take it to be log n, for example. It's not very important as long as it's not too big. So as long as it's not more than some polylog amount. Now, why do we want to think about non-compressors? It turns out that these are a natural object, which are still somewhat expanding in flavor. Just intuitively, we're already kind of close to expansion by getting non-compression. But at the same time, this planted trapdoor is so compressing that it's clique-like. In fact, we're always going to take the right degree to be 2. So if we think of each of those right vertices as just representing an edge over its neighbors, then the trapdoor is precisely isomorphic to a clique. I'll give a little bit more details on this later. Any questions so far? Okay. Coming back to our roadmap, the only thing left is to describe how we go from planted clique to this intermediate object, and then to trapdoor expanders. looking at this in a little bit more detail, we want one algorithm starting from the left side on this diagram, one algorithm such that if we sample a graph from the unplanted GN1/2 distribution, when we put it through the algorithm, we should end up with another graph H, which is a non-compressor with right degree 2. On the other hand, if we sample a graph G from the planted Erdős-Renyi distribution, GN1/2 into the delta, and put it into the same exact algorithm, we want to end up with an output graph H that has a highly compressing small set. And we can say something analogous for the second arrow here, where we want the conversion from H1 to K1 and H2 to K2 through the exact same algorithm. Okay, let's continue working backwards. We'll look first at going from trapdoor non-compressors to trapdoor expanders. Let's consider just the case where we want to amplify this non-compression property to true expansion. And then I'll come back to the case of the planted graphs later. There's one naive way that we can enforce that at least any small subset R prime of the right vertices will have a larger neighborhood than what we started with. And for this, we just take every left vertex and duplicate it a polylog number of times to form a cloud associated with that vertex. And then now for every edge in the original graph, we're just going to have a set of edges which connect to each vertex in the cloud. You can see on the diagram here, if we have an edge between U and V, now we turn U into a cloud. In this case, I've taken polylog to be 5, but in practice, it should be a little bit larger than 5 at the very least. And we just have V connecting to each of those cloud vertices. Drawn an example with a graph that has a couple more edges. And it's not hard to see that at least the neighborhood size is now bigger than the size of the original set of right nodes. But there's a problem, which is that we're also increasing the arity, K. So we're increasing the degree of each of these right nodes. And in fact, it turns out that the degree is increasing at exactly the same rate as the neighborhood size. So if we want to get expansion in terms of the neighborhood being bigger than a gamma K times the original set size factor, then this approach is hopeless. But there's another idea, which is we can still do these vertex clouds. But now for every edge UV, instead of connecting to every vertex in the cloud, we're just going to pick a random small subset of the vertices in the cloud and connect to only those. Roughly speaking, this is actually related to the idea that random sparse hypergraphs are good expanders. And some intuition as to why this helps us in our particular case is that if we have a set of right nodes R prime, and there's some cloud which has few of those vertices connecting into the cloud, then those connections will be very spread out just due to the randomness. And we get expansion, at least locally, within that single cloud. Now, this isn't good enough for us to get to our full definition of expansion, but it turns out that actually this already satisfies a weaker notion, which unfortunately I don't have time to go into right now. But the moral is that we're getting a little bit closer to our goal. Unfortunately, we have a very critical obstruction, which is that an adversary can just take any cloud on the left side and just look at its some of its neighbors on the right side. I've drawn that in the picture here. And now I argue that this set of right nodes is at least not expanding enough for our purposes. The reason for this is that each right node connects to exactly 2 clouds. Remember that we're taking D equals 2. And one of those clouds could be totally spread out from everything else, but one of those clouds is going to be common to all of the other vertices. So you can imagine that we are oversaturating this one specific cloud. And now the edges going into that cloud are not really going to contribute anything to increasing the neighborhood size. So at best, we can hope that about half of the edges coming out of our set R prime will make the neighborhood larger, but this isn't enough to get a 0.99 factor expansion. Because for 0.99, we need at least 99% of the edges going out to contribute to expansion. So our final idea is to increase the arity on the right side before doing this cloud augmentation, but in a very careful way. To describe this, we're going to go through a couple conversion steps. For the first conversion step, we're going to look at the original graph H and produce another graph H prime, which is not bipartite. The way we do this is by looking at every right node in H and just interpreting it as an edge over the left nodes. In this diagram, we can take the example of the first right node. It connects to left nodes B and C. So in our graph H prime, the vertices B and C are connected by an edge. And for reference, we've just labeled it by a 1. Now we're going to convert from this graph to, again, a bipartite graph, H double prime. But now we're going to encode incidence between triangles and edges, or more generally, X cliques and X minus 1 cliques. This is different from the original graph because morally the original graph is incidence between edges and vertices. So we're going to sort of higher order cliques.
And just a quick question. So for the case of like d equals 3, it's like a hyper edge, or does it not generalize this case?
Yeah. For d equals 3, it would exactly be a hyper edge.
Okay.
For our case, we only need to think about the d equals 2 case
Right.
for now. Yeah. Okay, any other questions before I describe some of the last steps? All right. We can look at this with our example again. And I'm just going to take the case of triangles and edges for now. We can see that H prime contains exactly 2 triangles. One of them has the edges 1, 3, 5. So we have a vertex for that on the right side. And then we have a vertex for the other triangle. Now, each of the left vertices in H double prime just corresponds to an edge in H prime. And now the connections in our final graph, H double prime, are encoding precisely the edges that were in the triangles in H prime. Okay, any questions on that conversion stuff?
So basically you're like adding like another third layer of vertices that represent triangles.
Yeah.
Why is like, I guess like how is this natural to get smaller arity, I guess?
Well, we actually want to increase the arity.
Sorry, well, how is this natural to increase the arity?
Well, okay, I'll get to that in just one slide.
Yeah, okay.
Just one slide. Okay. The last step is that we're going to use the same idea as in idea 2. We're just going to take our final bipartite graph H double prime and do this sparse cloud augmentation. Okay, so the reason that triangles and edges are helpful is because of the observation that 2 triangles in H prime can share at most 1 edge. If they share 2 edges, then they become coincident and they're not distinct. So now the observation is if we try to do the same adversarial construction where we pick a cloud and then we take its neighbors on the right, now we can only force these right vertices to share 1 common cloud, but now each of them will go into 2 other clouds. So you can imagine, morally speaking, we get an expansion factor of about 2/3 times k. Yep. And actually, it turns out this adversarial construction is basically the best possible. We show via a set of rather interesting inductive arguments that the expansion is basically 2/3 in the case of triangles versus edges. And if we want to get a 0.99 expansion factor, for example, we would do 100 cliques against 99 cliques. So in summary, our algorithm, when given an input non-compressing graph H, is going to first do this incidence graph trick between cliques of different sizes. And then we'll use the clouds and the random edges to boost from that to expansion. The output is just taken as the graph K. But now let's return and talk about H2. We want that if we apply this exact same algorithm to the case that we have a planted compressing component, then we still have a small component which is at least somewhat compressing. And the key observation here is that we mandated that H2 has a component which is just maximally crazy compressing. So we're okay with losing a lot of this compression, and as long as we have at least a little bit of compression at the end. In particular, let's look at this conversion from the graph H to the graph H prime, where again, we just interpret each right node as an edge. Now in H prime, the vertices which were in the neighborhood of our trapdoor now exactly form a clique. And now this clique is so dense that even when we do this small clique inclusion graph, and even when we augment with these slightly, well, the clouds are very small. So even when we augment with these polylog sized clouds, we still get some amount of compression. Okay, any questions on that? Perfect. Now the only remaining step is to discuss how we go from planted clique conjecture to these trapdoor non-compressors. And for this, we turn to a famous algorithm called the randomized graph product, which was first discussed by Berman and Schnicker in 1992. Consists of a few steps. So given a graph as input, we will define a new graph, G prime, on a new vertex set and a new edge set via the following algorithm. The first step is that for each size L clique in the original graph, we now have a vertex in the new graph. If we just take L equals 2, then these L cliques are precisely pairs of vertices that have an edge between them. In our original graph G, we have 4 such edges, thus 4 such pairs of vertices, and V prime has exactly those as its vertices. Okay, and for the second step, we're going to delete nearly all of the vertices that we just put in V prime. In particular, we delete them with probability all but an inverse polynomial or even an inverse superpolynomial in the size of the original vertex set. In our toy example, this means that we expect to delete all of the vertices, but you can imagine that if we start with a graph with 1,000 nodes, or for example, 100,000 nodes, then we'll maintain at least a small number of vertices, even after the deletion. Then the final step is that for the remaining vertices, we connect U prime and V prime, if and only if their original cliques in G together induce a clique when you take their entire vertex set. Okay, so going back to our example with L equals 2, we're going to assume no deletion because otherwise there's no vertices. I'll just discuss the edge, which is between the vertex labeled AB and the vertex labeled BD. If we look back in G, this gives us a vertex set A, B, and D. And together these form a triangle, which is a clique. So that's why we have an edge between them. And an important note here is that we're okay with the vertex sets overlapping a little bit. The only stipulation is that together they form a clique. Now, I note that this algorithm has been used several times in the hardness of approximation literature. For example, actually by the papers I mentioned at the beginning, by Alon and co-authors and Anarangzi and co-authors. But it appears that we analyze it in a new context because our goal is to get these trapdoor non-compressors. Okay. Any questions before I move on to discussing, roughly speaking, the analysis? All right. Our goal is to use this randomized graph product to effectively lower the local edge density.
I was wondering, since you apply just this algorithm, what is the quality? I mean, to what extent you rely on this algorithm, like because the output is still dependent on this algorithm that you do. Like, does it? I mean, as long as. So the algorithm is still part of the construction. So in some sense, you still rely on this construction of random graph from this specific G graph.
Yeah, so
you have removed a bit some properties of G, construct G prime.
Yeah, we're gonna use G prime as like our new graph to get the trapdoor expanders. So we just forget about G after we do the randomized graph product. I don't know if that answers.
So you're never concerned about the fact that G prime is not a random graph with the same property. It's like the output still of.
Yeah, so this is precisely why we need to assume that sparse k-LIN is hard even for non-random graphs, as long as it's expanding enough. And like we mentioned in the very beginning, there's a couple like pathological cases, but we still have enough entropy inherited from the original graph that it's still random enough to be hard. Yeah, but that's a very good point. Okay, so let's say that we sample our graph G from the unplanted error-to-training distribution Gn1/2. Now we're going to let G prime be the randomized graph product where we take the input graph and then we take some small but super constant parameter L. And we also have this deletion constant C, which is just arbitrarily small, but it needs to be a constant. And we want to argue that this new graph G prime, roughly speaking, acts as if it were sampled from the error-to-training distribution with a vertex set now of size n to the theta L, and then a much lower edge probability. Importantly, the fact that we're now getting a much larger graph, in fact, a super polynomially larger graph, is why we need this slightly quasi-poly hardness of the Planck-Clique conjecture. Okay, to understand this, we'll make a couple observations. The first one is that when we do this deletion process for the vertices, this is step 2 in the box up there, we're killing off so many of the L cliques that if we look at any small set of vertices in G prime, they map back to cliques in G that are, loosely speaking, disjoint from each other. And in fact, we can show that the amount of overlap that they have is within a constant factor of if they were just totally disjoint. So they can't compress by more than a constant factor of being totally disjoint. And the second observation is that because most of these original cliques in G are spread out from each other, every edge in G prime requires us to have a lot of edges all simultaneously existing in G. They have to connect one L clique to another L clique. And now we can use these observations together to show that for any set S, being a subset of the new edge set, with this subset of the edges being small enough, it will have to cover at least the size of the set divided by log n vertices. So roughly speaking, what this is saying is that any small enough set of edges in G prime can't collect on just a small number of vertices. It has to be almost completely spread out with respect to the vertices. It's a little bit different way of looking at the expansion. We need to look at the edges first and then the number of vertices that they cover. Okay. But now notice this cutoff. Well, it isn't exponential in L. If we take L to be a constant, then we still only get this guarantee for constant size sets. So this is why we need to take L to be slightly super constant. Okay, and now we can just take the bipartite edge vertex incidence graph for G prime as the output graph H. This is just the conversion that I've already described a couple of times now. Looking at it from this pictographic format, every right vertex in H will just be indexed by an edge in G prime, and every left vertex is indexed by a vertex of G prime. And it's right to regular, as we require. So to summarize at a very high level, if we start from G from this unplanted distribution, the first step is to use this randomized graph product to lower the local edge density. And then we just take the edge vertex incidence graph as the output graph H, and it has non-compression. Now let's just quickly return to the case that G was sampled from the actual planted distribution. It turns out that as long as this constant C is less than the exponent in the clique size, it's not hard to show that even after the deletion, many L-size subcliques of our planted clique will be retained. And then as long as we retain at least some of the L-size subcliques of the original planted clique, they will together induce a clique in G prime. This is because we're not doing any edge deletion. So all of the subcliques of the planted clique are, of course, going to form cliques themselves, and thus they're all going to be connected in G prime. And then now it's simple to see that when we do this extension to the graph H, we'll have this highly compressing trapdoor just as we require. Any questions on what I've discussed? Okay. Just looking at it from the graph perspective one more time, we get this trapdoor T, and it has a very compressing neighborhood. Now we have the complete scheme, at least summarized. We go from the planted Clique conjecture to trapdoor non-compressors via this randomized graph product. Then we use Clique inclusion and sparse clouds to get trapdoor expanders. And then we can combine this with sparse k-LIN using previous work to get public key encryption. In conclusion, we make the first non-trivial use of the planted Clique conjecture for building public key encryption. And more generally, we hope that our work and future work can help to revitalize this field of combinatorial hardness for public key encryption. Thank you so much for listening.
What was the cognitive structure that was used in the work of Applebaum, Barak, and Wigderson?
Oh, I'm sorry, the like assumption they used?
Yeah, like what?
Yeah, but well, basically their assumption is saying, I'm gonna go back to trapdoor.
Put in bipartite graphs.
Yeah, well, they're just directly assuming the existence of trapdoor expanders. So basically, they're saying if mode 1 is a totally random graph, and then mode 2 is a totally random graph, but where we plant a trapdoor with exactly this property, then they should already be indistinguishable. So we can sort of see our work as like substantiating the fact that that problem should be hard. Yes.
Also, you're reducing the noise for the LPN type of them.
No, they also do that.
Yeah.
The graph assumption is precisely for that.
Wait, but did they reduce it to polyglot, like Ebers polyglot?
They can reduce it to any.
Yeah, they can take the same error
Okay.
that we took.
If I understood correctly, the security tools mentioned at the beginning, you said that the tricky part was to say that mode 1 and mode 2 are, like, let's say, indistinguishable in what they produce.
I'm sorry,
at the
say
very beginning, when you describe the sketch of security for the construction, the PK construction, you'd say that as long as you have these two modes that are indistinguishable, then the rest directly follows from the k-LIN assumption in the hybrid, because once you have this indistinguishability, but how do you formalize it in terms of like what is the security notion behind like not distinguishing the two modes?
Oh, yeah, good. So
because I'm not familiar with this, so just
I can actually draw it quick if you want. Fortunately, I don't have a backup slide. So let's say that our graph A, let's say that this is sampled from mode B, or mode 2. So this is the planted mode. First, we use the indistinguishability of mode 1 and mode 2 to say that, okay, this is computationally indistinguishable from A and AS plus B, where this is now from mode 1.
yes, my question was on the indistinguishability between mode 1 and mode 2.
Yeah. Oh, like you were just saying.
Yeah.
Can we assume this?
I mean, how do you prove it? Like, you prove it under the fact that under the quantitative assumption, right?
Oh, yeah.
So this was my point. Like, how do you?
So the key idea is that if I go to this slide, we start from this planted clique distribution where you either have a totally random graph or you have a random graph with a planted clique. And by the conjecture, these should be indistinguishable. Now we just apply one algorithm to like an input graph. We don't know if it's planted or not. And that gives us this like compression versus non-compression dichotomy. And then now we apply the same algorithm again to get out this expander versus non-expander.
It's very basic.
Yeah.
But that you just apply the same algorithm for both.
Yeah. It's nothing more than just the observation that it's
Okay,
identical. Yeah.
So yes, I got you after this because you said in your slide that once you have the indistinguishability with mode 1 and mode 2, the rest is like mostly okay in terms of security.
Yeah.
Okay.
Any other questions?